Good morning, everyone. My name is Isabel Ruby, and I'd like to talk to you today about a new technique for molecular mapping. So essentially, the idea here is that we're going to use a novel pulse sequence to determine J coupling that is smaller than the line width of a signal. You could go to the next slide, please. So for those of you on the call who aren't super familiar with what NMR or nuclear magnetic resonance is it's a tool used, you're probably more familiar with it as MRI in the medical field. And it's often used in chemistry to identify unknown compounds, so structural information. So for example, if you're in an organic chemistry class, you're often given a proton NMR spectra and a carbon-13 spectra, and you're told, figure out what you have. And from those two spectra, you can actually do a pretty decent job of narrowing down the compound you have, especially if you're given a list. There are some limitations on this as you go to larger and more complicated structures, though. And I want to talk to you a little bit about J coupling. So if we could please go to the next slide. So I've just blown up a common one-dimensional proton NMR structure here, spectra here. And I hope there's no one on the call who is red-green colorblind. If you are, please let me know, raise your hand, and I'll be more specific. But it's this is an ethyl acetate molecule, and it's been helpfully color-coded. So you can see the green hydrogens on the far left carbon relating to that middle tall signal. It's essentially a singlet, just one peak. And that's because there's no hydrogens on the adjacent carbon. There's no J coupling, which is basically a measurement of, you can think of it as interference. When you have your sample in the NMR, there's a strong magnetic field in one direction, and you apply a pulse in another direction, knocking all those spins off kilter. And the measurement is essentially the time it takes for the spins to return back to that strong magnetic field. But as they're all relaxing back, the nearby spins, so those green hydrogens are not being affected so much, but the red hydrogens and the blue hydrogens are being affected by each other. So it's causing this splitting occurrence. And there's a rule, an n+1 rule. So you can see the blue hydrogens are split into essentially a triplet, because there's two neighboring hydrogens, 2 + 1, n+1, 3, and the red hydrogens, there may be two of them, but there's three neighbors, and so that causes it to split into 4. We can go to the next slide, please. So what do we do when you can't see those splittings? Because it gives a lot of information about what kind of elements and atoms are nearby. So the idea is to use a new pulse sequence. The pulse sequence is essentially what you're feeding into the computer to tell the NMR, say, hey, I want to do apply this pulse, and it'll knock the spins off kilter this way. And depending on your pulse sequence, you can change the clarity and resonance of your signal. So the pulse sequence that Dr. Fu has suggested starts with cross-polarization. So protons are really easy to see. They're really strong signal, but things like nitrogen-15, not so much. So you cross-polarize to strengthen the signal from the nitrogen. And the idea is to use selective pulses where you're only hitting a few spins and then a hard 90 followed by another selective 180-degree spin. And what that means is essentially you're knocking your spin from, let's say, we have a little picture of the Z and Y axis, ZXY axis at the top. So if you're starting on the X axis, you knock it 180 degrees to the -X. Except, fun fact, if we're sending all our pulses from an X direction, it won't affect anything with an X signifier on it. But anything that's Y or Z is fair game. So a Y will go to -Y, Z will go to -Z. And a 90-degree pulse, well, that's a right-hand rule. For those of you who have taken physics, you point your thumb in one direction, you curl your fingers in the other direction, it'll tell you where things are moving. And in the bottom right, we have an image of histidine, which is the protein that we'd be using for these measurements. So you can see here, the nitrogens are what we're concentrating on, right? There's two that are in a ring together. Those are close by. They're going to have J coupling with each other. And then there's a third nitrogen, which is farther away. But there's some interesting things happening where if you were to spin that ring around so that the nitrogen with the hydrogen on it was closer to that far left nitrogen, you could see how there could be some hydrogen bonding in between those two. And so we're using a theory from an earlier paper that measured that coupling to base off our, to compare the results to. So if we could go to the next slide, please. So the product operator is how we're going to confirm any results with the math. And I just wanted to take a brief moment to talk through how you do this math a little bit, because anyone can do it if you take the time. And it's so here I started with IXI. So the capital I is your product operator. The little x is the direction in the field. And that little uppercase, or the little I up top, the superscript, that is saying spin I. So if you have a 3-spin system, I, J, and K, we're selecting for I and J and not selecting for K, those selective pulses. So every time there's a time delay, you have to evolve the spin. So first you go through the IJ coupling, the JK coupling, and the IK coupling. So if you're just looking at IXI, it'll evolve an IJ coupling because you've got that I signifier on there. So you keep the product operator the same, you tack on a cosine term, you rotate the product operator to IY and IZJ and tack on a sine term. So far, so good. Then you're going to go through JK evolution. There's no J terms except for the only J is on a Z term. So that Z basically says no bueno, we don't evolve. So then you have to take it through IK coupling. Now this, you can see every time one term turns into two terms turns into 4. So there's a reason why I'm not showing you my actual set of terms, that the final set on the screen is because there's over 100 in that final calculation. We could go to the next slide, please. So in conclusion, the math is going to helpfully elucidate what's going on in the actual signal. I didn't want to ask Dr. Fu for any of the results because I don't know if that's appropriate to share yet. We did see some signal where we were expecting 2 of the signals to change and 1 to not. But I think that the third one, which ends up changing when it should not, is in fact due to the fact there are some anti-phase terms from that third non-selected spin in the final set of terms. So at the moment, what we need to do is, 1, I need to go through that 100+ terms and make sure I don't have any calculation errors. And 2, I want to take a look at seeing if I can calculate the final term sequences for a different pulse sequence. So instead of having selective 180s and a hard 90, do hard 180s and a selective 90, or selecting just the I and J spins at all 3 points. So the idea, I know that this, as it says, new technique for molecular mapping, you're going, what does that got to do with anything? Well, the idea is that you could use this to figure out structural information, like from that first 1D spectra we looked at, and you could say, oh, if I see a four individual peaks and 3 individual peaks, those could be next to each other because that could be, there's 2 coming from here and 3 coming from there. So that's the correlation, is that information you get from the splitting. And unfortunately, with some signals, it's too narrow to see the splitting. So hopefully, by doing this pulse sequence, we can get that information. And I'd like to thank Dr. Fu. I'd like to thank Professor Wong. I'd like to thank the MagLab for hosting us. And of course, I'd like to thank everyone in the REU program, Kawana, Carlos. Y'all have been excellent. Thank you so much.